Hi everybody, welcome to this video on truth tables. Last time we learned how to symbolize English statements into our language of symbols so that we could use those symbolic versions of statements in truth tables. This truth table method that we'll be learning is going to allow us to determine whether arguments are valid or invalid, and it's a very powerful method. So what is a truth table? This here is an example of a truth table. More specifically, this is a truth table that shows the meaning, the definition of our logical operator for not, the negation, or tilde here. On the left, you have a vertical column where you have a lowercase italicized p. Think of this lowercase p as a variable. It could stand for any kind of statement. Any kind of statement that we'll be using. So it could be an atomic statement or a compound statement. So P as a variable, say it could stand for the atomic statement B. P could stand for the compound statement, say if C then H. It could stand for a very complex statement, L or G and S, only if R. That's a whole long compound statement. And P is a variable that could stand for any statement in our language, whether it's atomic or compound. Now, the true and false below it represent all the possible truth values that the statement up here could have. Obviously there's two. It could be true or it could be false. So P represents this statement could be true or it could be false. So this is every possible combination. There's only two. Then over here on the right, we have the negation of P. And the false and the true below it, the F and the T. The F and the T stand for false and true. These represent the truth value of not P when P has the corresponding truth value over here on the left. So when P is true, not P, of course, is going to be false. And when P is false, not P is going to be true. Now, this truth table for negation, of course, is very simple, but some of the truth tables for other logical operators might be a little bit more, might be more tricky. Now, the main idea behind truth tables is that they are truth functional. That is, so what does it mean to be truth functional? Well, this is a nice definition to have. A compound statement is truth functional if its truth value is completely determined by the truth value of the atomic statements that compose it. What does that mean? Well, take this statement for example. 2020 is not a fun year so far. Sad. Well, how would we symbolize this? We can use this scheme of abbreviation. We use the capital letter Y to stand for the atomic statement. 2020 is a fun year so far. And then the only thing we need to add to symbolize this is going to be a negation, right? Because we got that negation in there. So we symbolize our original statement as not Y. Now, is not Y true? Is it false? Well, whether it's true or false is going to be completely determined by the truth value of Y. Whatever the truth value of y is, you plug that in and you're going to get a certain truth value as a result. So if we make a truth table for this complex statement, we would do it like this. We're going to draw our little graph like we did up here, and over on this side we'll put the statement, the compound statement, under consideration, and over here we're going to put all the atomic statements. So there's only one, so we'll put y. Now there are of course two possible truth values that y could have. It could be true or it could be false. Pretty simple. Well, when it's true, not y is false, and when y is false, not y is true. And that gives us every possible truth value that not y could have. There is no other factor other than the truth value of y. There's no other factor to whether or not y is true or false. So we say that it's truth functional. Now let's look at a truth table for other logical operators. The truth table for negation is pretty simple, but some of the truth tables for other logical operators can get a little bit more complex. So let's do one for conjunction. So the dot, right? It's gonna need to be a little bit bigger. We'll go ahead and write a conjunction over here. So we'll write P and Q lowercase. So P could stand for any other statement. Q could stand for any other statement. These are just stand-ins for any statement. Now over here, we need to write every possible truth value that our atomic statements could have. But because there's not just one, there's two statement variables, we're going to have more combinations, right? You could have P is true and Q is true, or you could have P is true and Q is false. You could have P is false, Q is true, or you could have both of them false, right? There's not just two possible truth values. Because you have two variables, you need to account for every possible combination. So we get 4 possible scenarios. Well, what happens to our conjunction on each of these scenarios? Well, when they're both true, of course, this is going to be true. When one of them is true and the other's false, it's going to fail to be true, so it's false. It's also false if which one is true is switched, and of course, if both sides are false, the whole conjunction, the and, is going to be false. All right, so to see this, let's do an example. In this example statement, we have a conjunction, an and. Steve is swole and Patrick is pumped. Is this conjunction true? Is it false? Well, this compound statement could be represented by the P and Q up here. So if, say, P is true, say it's true that Steve is swole and it's true that Patrick is pumped, then is this whole statement true? Steve is swole and Patrick is pumped? Yeah, it's true. What if one of them's false? So it's still true that Steve is swole, but unfortunately Patrick is not pumped. Well, is this whole statement true? Is it true that Steve is swole and Patrick is pumped? No, because unfortunately Patrick failed us. So the whole statement as a whole is false. Of course, if we reverse which one is false, that doesn't change anything. Still, the whole statement's going to come out false. And of course, if both are false, it's false that Steve is swole and it's false that Patrick is pumped. Of course, this whole statement, Steve is swole and Patrick is pumped, that whole thing's false, right? So the conjunction still is pretty straightforward. That's how conjunction works. It needs both parts to be true in order for the whole conjunction to be true. If any one part is false, the whole thing is going to be false. Disjunction. This one is also a little bit complex. So take, for example, Beth is bored or Renee is representing. Now, of course, we're going to interpret this either or as inclusive. So it's possible that it's true that Beth is bored and it's true that Renee is representing. It's not that only one can be true. They could both be true. This is just saying at least one is true. So what happens when we evaluate all the different possible combinations of truth? Well, for P will represent Beth is bored. And then Q is going to represent Renee is representing. So of course they could both be true, right? It's true, Beth is bored, and it's true, Renee is representing. Well, of course, the disjunction is going to come out true. What about if it's true that Beth is bored, but unfortunately it's false that Renee is representing? She's just not representing lately. Well, this either or is still going to come out true, right? Because either or, it just needs at least one side to be true for the whole thing to be true, right? So, and of course it doesn't matter which one is true. If it's true that Beth is bored, this whole statement is true. Also, if it's true that Renee is representing, well, the first part's false. Well, that's all it takes. The whole statement's true. But of course, if both of these are false, Beth isn't actually bored, Renee isn't actually representing, then this whole statement is going to come out false, right? It's false that Beth is bored or Renee is representing. So notice the comparison here. If we compare disjunction to conjunction, the or to the and, it's real easy for or to come out true. In fact, it's always going to come out true unless that one case where both parts of it are false, right? So it's real easy for an either or to be true. You got 3 trues and a false. Well, conjunction, you got 3 falses and a true. It's a lot harder for an and to be true. You got to have both sides true. So it just takes one failing and an and is going to come out false. Now let's do conditionals. Conditional statements have one of the trickier truth tables. You'll see what I mean. Take this statement. If you get an A, I'll send you a box of cookies. Not me, but imagine your mom says this. In fact, imagine mom promises this. Mom promises to you, if you get an A, I'll send you a box of cookies. Well, is this conditional? So the P will be you get an A. Q is going to be mom says, I'll send you a box of cookies. What is the truth value of this given each scenario? Well, say you do get an A and mom does send you cookies. Well, then the whole conditional is going to be true. If, however, you get an A and then mom doesn't send you cookies, well, then that's going to be false. What about the other two? Say you don't get an A. Unfortunately, you got a B, maybe even a C, probably a B. But you don't get an A, so it's false that you get an A. But say it's still say mom still sends you cookies. So that part's true. She sends you cookies. What's this going to be? Well, it's actually still going to be true. What about if you get that B, so you fail to get the A, and unfortunately, mom doesn't send you cookies? Well, the whole conditional is still going to be true. Now, this might strike many people as surprising that we get true and true down here when we have false and false in the antecedent, the if part. But to help you think about it, think about, does mom break her promise on each of these scenarios? If she keeps her promise and she doesn't break it, then the conditional, the if then, is going to be true. The only way for this conditional to be false is if mom breaks her promise. Well, on that, there really is only one way for mom to break her promise, right? Because her promise is conditional. If you get an A, I'll send you a box of cookies. If you say you don't get that A, you get that B, and so guess what? Mom doesn't send you cookies. So that's like false, false, right? It's false that you get an A, and it's false mom sends you cookies. Did mom break her promise in that case? No, because you didn't meet the condition, you didn't get the A. So the whole conditional if then is still true, right? Because mom didn't break her promise. What about on this row number 3? Say you don't get the A, so it's false that you get the A, but mom's real nice and she sends you cookies anyways, right? She went above and beyond. Well, did she break her promise? No, she didn't say anything about what would happen if you don't get an A. She's still free to send you cookies if she wants to. So she didn't break her promise. So we'll mark that if then as true. In fact, there's only one way for mom to break her promise, right? Is if you fulfill your part of the condition, you do get that A, but then mom does not send you cookies, right? Then she broke her promise. So that's the only possible combination, only scenario where mom breaks her promise. And likewise, for conditionals, that's the only scenario where a conditional comes out false. Every other scenario comes out true. So if you are ever confused about conditionals, always go back, my suggestion, always go back to the idea of promise. Did the promise get broken? Imagine the conditional as a promise. If the promise is broken, it's false. If the promise is not broken, either because everyone fulfilled their part or the if part was not met, well, the promise wasn't broken, right? Because the conditions weren't met. So always go back to promises if you get a little lost thinking about conditionals. Let's compare this truth layout to what we've seen so far. Here, remember, we only have one way for it to be true. Either or, there's only one way for it to be false, right? If both sides are false. Well, down here, there's only one way for a conditional to be false. It's if that promise is broken. So it's real easy for a conditional to be true, much like it's real easy for an either or to be true. So they have that going. But which combination is it? It's the second combination where it's false. So true, false. However, up here, the one where it's false, you have to fail on both counts. So it's helpful to think about and compare so you can really get it in your mind what the truth conditions are for each type of statement, because you'll really want to know that for the problems going forward. Finally, let's look at biconditionals. We have this example up here. Sanders wins the nomination if and only if Biden loses the nomination. Okay, what do we do with that? So P will be Sanders wins the nomination, and Q will be Biden loses the nomination. Well, let's say both of those are true. Let's say it's true that Sanders wins, and it's also true that Biden loses. Well, is the whole thing going to be true or false? Well, it's going to be true. Both sides are true. What about if it's true, Sanders does win the nomination, however, it's false that Biden loses, right? It's false that he loses. Well, what does that mean? Biden wins? We'll say that. So then that would mean Sanders wins the nomination and Biden wins the nomination? Well, then this whole statement, I mean, if that's possible, if it's possible for them both to win, I don't know, maybe the rules have to change, then this statement actually is false, right? It's false. Sanders wins the nomination if and only if Biden loses. That's false because it's possible they could both win. So this whole biconditional is actually false. What about if we switch the truth values around? Say it's false that Sanders wins. So if it's false that he wins, then he loses, I guess, right? And we'll also say it's true that Biden loses the nomination. Maybe another candidate wins and they both lose. Well, if it's possible for them to both lose, then this whole statement is actually false, right? Right? It's not the case. Sanders wins the nomination if and only if Biden loses the nomination. That doesn't work, right? Because it's possible for them to both lose. Okay, what about the last one? The last one might seem a little odd. It's false that Sanders wins the nomination, right? So he didn't win, Sanders didn't win. But it's also false that Biden loses. So I guess Biden wins. So I guess Biden wins and Sanders doesn't win. Well, then this whole statement works. It still works, right? Nothing was violated. So it's actually going to come out true when both parts are false. That might strike you as odd, but this is how these work. I'll explain in a moment in terms of a biconditional as two conditionals together. But notice the pattern here. You've got a biconditional is going to be true half the time. So it's true basically when both sides have the same truth value. If both sides are true, well, that works. The biconditional is true. If both sides are false, well, that still works, right? Nothing was broken. It's like both sides of the biconditional are tied together. They got to have the same truth value. If they get the same truth value, then the whole thing works. It comes out true. But if you have a mismatch, one side's true and the other's false, well, the biconditional is going to fail. It comes out false when you have a mixed match. So now let's think about biconditionals in terms of two conditionals together. To better understand biconditionals, let's look and compare a biconditional to something that's actually logically equivalent to it. So here we have our standard truth table for a biconditional. In this case, we used actual statement letters. So we have S and O. S if and only if O. So this is just going to be the same as right here, right? Here's every possible combination, both true, one true and one false, right? One true, one false, both false. So this is the same as here. Let's compare the biconditional to a conjunction of two conditionals. So we have this conditional, which is like this biconditional, but one side of it, so if S, then O, right? If S, then O, but also going the other way. If O, then S. That's like going from if O, then S. And that's basically what a biconditional means. So let's see what results we get. Well, if S is true and O is true, then this conditional is going to be true. Let's just do this conditional for now. If S is true, O is false, well, that's the broken promise, right? So then this conditional is going to be false. And if S is false, O is true, there's no broken promise, so this conditional is true, and then if both are false, of course, no broken promise. Now let's do the far conditional over here. If O is true and S is true, of course, these are still, the conditional is true. If O is false and S is true, then there's no broken promise, right? Because we're saying O is false and S is true. So we're going false, true. So no broken promise. What about this line? O is going to be true, and then S is going to be false. Well, that is a broken promise, right? O is true and S is false, so broken promise. What about if they're both false? Well, you can't break a promise in that case, so it's true. There's only one line right here where there's a promise broken for that conditional. Okay, now we have both conditionals mapped. However, the main operator for this compound statement, the main operator is the and, right? It's saying this conditional and this conditional. In order for this whole statement to be true, since it's an and statement, a conjunction, it needs to have both sides true, right? You got to have both sides of an and true. The whole thing's true. So let's go ahead and write the truth value of this whole statement. Well, both sides are true here. So in that scenario, the statement's true. Unfortunately, here we have one side false. So the statement's false. True, false. So one side of the and is false. So the whole and statement is false. And here, oh look, both sides of the and are true. So that makes the conjunction of them also true. So this right here is the truth value on each possible combination of this statement. And of course you can see now that it's exactly parallel to the chart, the truth table for the biconditional. So every time the biconditional is true, this conjunction of two conditionals is true. Every time it's false, the conjunction of the two conditionals is false. So what this shows is that this biconditional is logically equivalent to this conjunction of two conditionals, one basically going each way that the biconditional does, and putting them together. So that's maybe one helpful way to think about a biconditional. The biconditional is just saying this conditional is the case, so if S then O, and if O then S. And so it ends up with the result that it's true when both sides of the biconditional are true, and it's also true when both sides are false. It only fails when you get a mixed value. Now let's do a few exercises from the exercises in the book to test our knowledge. So this is 7.2, the exercise set A. It's on page 310. This one it'll give us a statement, and it asks us to determine whether the statement is true or false. And it gives us the truth value of the atomic statements. So for all of these, the A's will be true, the B's will be true, and then C's and D's, they're both going to be false. So we got to use that information to determine whether or not the whole compound statements are true or false. So let's see if we can do it. Go ahead and try to do it on your own. You can pause the video and see if you get it right. So the first one, number 2. So if A is true and C is false, what does that make the whole thing? So we got A true, C false. Well, it's an either or. So in order for this whole statement to be true, all we need is one side true. That's all it takes, right? So we got one side, so this whole one is true. Number 8, all right, we got A, which is true. B is true. So if A is true and B is true, well, the conjunction A and B, that's going to be true, right? So we'll write the true underneath the dot. Excuse me. Now, what about the whole statement? Because the whole statement is a negation, right? It's the negation of everything in parentheses. Well, what's in parentheses? A and B. Now we've determined that A and B, that statement, is true. So the negation of something true is going to be false, right? If you make a statement that's true, well, if you deny the statement, then your denial is going to be false. So our whole statement comes out false. Number 12. All right, we got another negation. This is a negation, this time of a conditional. So, all right, so we know D is false, A is true. So what does that make this conditional? Well, there's no broken promise, right? So it's like you didn't get the A, so but then mom sent the box of cookies anyway. So she didn't break her promise. So no broken promise. So this conditional is true. And just like in the last example, if this conditional, the thing inside parentheses, is true, the negation of something true has to be false, right? Can't deny a truth. Your denial would come out false. So number 12 is going to be false. Number 15. This one looks a little maybe tricky. We've got a conditional inside parentheses, and then we've got a conditional that's made up of, this is the if part and this is the then part. So this is the main operator, right? Because everything else is in its scope. An if-then needs an if part and a then part. This whole thing is the if, and the D is the then. So this is our main operator. That's the truth value we're looking for to determine if this whole statement is true or false. So you always want to start from the inside and work out when you're doing something like this. The thing on the outside, this is going to be the truth value for the whole statement. So we know C is false and A is true. So that's going to make this conditional inside the parentheses. It's going to make that true, right? Because there's no broken promise, right? It's like mom sent the box of cookies even though you didn't get the A, right? So she didn't break her promise. Now, what about this whole conditional? Well, the if part we found out is true. D from what's given is false. So now we look at the if part is true and the then part is false. So is there a broken promise? Yes, in fact, there is a broken promise, right? It's like you did get the A, but then mom failed to send the cookies. So there's a broken promise. So this conditional is false, right? Number 21. This one is even more complex. this one is a negation of everything inside the brackets. So that's what we're looking for. The truth value under the negation that's the main operator. It's going to tell us whether this whole statement is true or false. It has the largest scope because it's negating everything. All right, so we start from the inside and work out what's the most inside thing. Well, inside the brackets, we have a conditional, right? The conditional is if A, then this whole thing. Well, inside these parentheses here, that's the innermost part. So we'll start there. So C is false and B is true. So what does that make this either or? Well, it's going to make it true, right? For an either or, you just need one side to be true. So we got that. So the either or is true. Okay, let's figure out this conditional now. We know the then part is true. A, we know from our given, is also true. So this conditional has a true if part and a true then part. So no broken promise. So the conditional's true. But now we need to move all the way out to the main operator because it's talking about everything else. If the bracket is true, then a denial of something true, well, that's going to be false, right? So number 21 is going to be false. Now let's do a few problems from section C. So 7.2C, this is on page 311. In this exercise set, we are asked to assign truth values to the atomic statements in order to make the whole compound statements come out false. So how are we going to do this? Well, we need so let's look at 2. The whole thing needs to come out false. So what do we look at? We want to look at the main operator, right? This whole thing comes out false. Well, it's a conditional. So we want the whole thing to come out false. Now, if the conditional's false, what does that tell us about each side of the arrow? Well, a conditional only has one way of being false, right? It's when the promise is broken. So to break the promise, you need the condition over here fulfilled, but then mom doesn't bring the cookies or doesn't send the cookies. So she breaks her promise. So you need to make the A, and then mom doesn't fulfill her part or what she promised. So there's a failing. So that means what? S is false. In order for this whole thing to come out false, we need S to be false. What about R? Well, we've said that not R, the left side of the arrow, is going to be true. So if not R is true, that makes what? R itself, it's going to be false. Cool. So this assignment of truth values to the atomic statements, we make S false and R false, and that's going to make this whole compound statement come out false. What about number 5? All right, we want this whole thing to be false. Well, what's the main operator here? Because that's the thing that's going to govern whether the whole thing is true or false. Well, the main operator is the thing with the most scope, meaning it's a thing that is saying something about everything else. Well, what about this biconditional? The biconditional needs something on the left and something on the right, and it looks like that leaves out everything outside these parentheses, right? The scope of this biconditional is just the T and the not W. So that's not the main operator, doesn't have the largest scope. Looks like the main operator is actually the V. So this has to be an either or statement. Either this whole thing on the left or the thing on the right. So we're trying to make the whole statement come out false. So we're going to say this disjunction is false. Now, if this disjunction is false, that means what about each side of the V? Because it's an either or. An either or needs what? Both sides of it to be false, right? Because it's either this or that. In order for that whole statement, either this or that, to be false, you need to fail on both sides. You can't have true on either side. So the right side needs to be false and the left side needs to be false. So we figured out now that T is going to be false, right? We're already partway there. So T is going to come out false. But we still haven't figured out W. Well, if this whole left side of the either or is false, right, the main operator over on the left side, within the left side, not the main operator of the whole statement, but the main operator just on the left side is going to be the biconditional. So we've determined that that's false. Okay, what does that tell us about each side of the biconditional? Well, how many ways are there for a biconditional to come out false? 2, right? You need a mismatch of truth values. If you have the same truth value on each side, it's going to be true. To get a false biconditional, you need a mismatch. Well, what do we assign to get a mismatch? Well, we've already figured out that T is going to come out false. And if T's false over there, that's going to be false over here, right? Can't be false in one place and true in another. So we know the left side of the biconditional is false, and we need a mismatch between each side. So if this side's false, the right side has to be true, right? That'll give us a mismatch. Now, the right side is not W. So that means not W is true. So if not W is true, W itself has to be false, right? So now we figured it out. W is going to be false. And that's all of our atomic statements in that compound statement. So when T is false and W is false, that makes this whole compound statement false. Good. We figured that one out. Number 11. Let's try to make this one false. Well, what kind of statement is this? What's the thing with the most scope? Talks about everything else. Is it the negation over here? Is that negating everything? No, it looks like the scope of the negation ends right at the closed parentheses, right? It's just negating the parentheses. It's not negating the rest. So this isn't it. That's definitely not it because it's inside the parentheses. So it looks like it's going to be the V over here. So this looks like another either or statement. So we need the either or statement. We're making it false, right? Just as before, we know that there's only one way for an either or statement to be false, and that's when both sides are false. So that means the right side is false and the left side's false. Well, the left side is, remember, this negation of the parentheses stuff. So we'll put the F for false under the negation, right? Because the negation of all this stuff, the left side altogether is false. Okay. Well, what have we figured out? Well, we've determined the right side of this either or is false. And the right side is not B. So if not B is false, then B has to be true, right? So now we know that B is true. We still need to figure out A. We don't know what that is yet. We can start filling some stuff in. I mean, B is true. So if it's true over there, it has to be true over here. And if B is true, then of course not B has to be false, right? So we know that much. We're trying to figure out A still. Well, we figured out that this whole left side of the either or is false, which is the negation of the parentheses stuff. So if the negation of the parentheses stuff is false, then the parentheses stuff itself has to be true, right? So the parentheses stuff is true. And we'll put the T under the main operator, which is the V for either or. So now we know within this parentheses, we got an either or that's true. We got one side of it that's false, right? The not B is false. So in order for this to be true, this either or, we know we need at least one side to be true. It can't be the right side. We've already determined that's false. So it must be the left side. The left side has, it's the only other side. So the left side has to be true. The left side is not A. So not A is true, which makes A itself come out what? False, right? So that is the assignment of truth values to our atomic statements over here that makes the whole compound statement come out false. So cool, we've completed that. That's it for this video. That was truth tables, the basics of how to do truth tables. Make sure to do the quiz that's for this module, the 7.2 module. There'll be a quiz for this one. And then make sure to do the homework. Hopefully the homework I'll have posted it by now. The homework will go up through this section of the book, 7.2. It'll be Venn diagrams, 7.1, which is the symbolizing, and 7.2, this one, truth tables. You'll be doing things like the exercises we just did. They'll also look out for any extra videos. I should be posting some extra videos soon related to this section, 7.2, and the previous one, 7.1. So there'll be that extra help and practice if you need that. What else? And then the next thing we'll do, 7.3, we'll begin using truth tables to actually evaluate arguments. So look forward to that. And thanks for watching. I'll see you in the next video.